In today's lecture, we will finally have a look at the seemingly impossible task of constructing spectroscopy with simultaneous time and frequency resolutions. To that end, we have to start with looking yet again, on the pump probe spectrum and the way how we detect the pump probe signal. So, pump probe spectrum, the scheme of measurement is such that we have a sample and we send several laser pulses to it. We actually sent two pulses, or we sent altogether two pulses, and one of them in our perturbation theory has been considered twice. That is the pump pulse, some EPU, that's the field that we sent in. And in our theory, pump probe experiment is actually characterized by the delay tau between the first and the second pulse of the perturbation theory to be equal 0, and both the first pulses, represented by one actual pulse, go from one direction. And then we have a probe going from a different direction, and the signal that appears goes together with the probe pulse. So in our theory, in the idea that we have about this theory, the probe plus the signal leave the sample. So there is probe pulse plus the signal, and by their interference we get apparently a decrease of the amplitude or decrease of intensity of the probe pulse. So altogether we can say that what comes out of the experiment, the electric field that comes out of the experiment, time dependent, is the probe pulse plus the signal pulse, and the signal pulse or signal, whatever is the length of that signal, let's not make any claims about that. We found in our previous discussions from Maxwell equations that this is going to look like some phase change, the frequency, and the polarization of the sample. The fact that none of these amplitudes here have spatial dependence is that we have actually already integrated that out. These are amplitudes. For instance, in the case of the signal of the pump, before it enters the sample, the amplitude is constant, so it does not depend on the spatial position. Otherwise, of course, we have the obvious factor e to the power of I k, which is a k vector in scalar product with the position vector. So these are integrated values. For instance, for the signal, this is an integrating values at the point where the field leaves the sample, because during the passage through the sample it actually integrates. We integrate Maxwell equation, and we also have a dependence of the signal on the width of the sample. So this is something that we have actually already done before, and all this is actually an instance of the so-called four-wave mixing, as we've discussed somewhere around the beginning of our lecture series. Now we will consider a frequency resolved detection. So typically we would diffract the signal and then look at the intensities of individual frequency contributions. So we basically detect Fourier components of the signal. Okay, which means that our E out should be understood as a function of omega, and that's the probe of omega and the signal of omega. And in fact, the same way we can write it using the polarization. This will be quite important. So we have the probe plus, of course, we are throwing away some constants that sit in front of the polarization. So let's put it all into some unknown gamma. We will not be interested in absolute value of the signal. So it's going to be some gamma I omega p of omega and h. And of course, these all quantities depending on omega here are basically Fourier transforms of the corresponding time-dependent quantities. Now, in our discussion of pump probe earlier, we assumed that we can write this nonlinear signal. I'm not actually specifically writing that this is a nonlinear signal, but it must be a third order signal because we are looking at the pump probe. We assumed that it can be written using some sort of a generalized susceptibility. So we assumed that P of omega can be written, well, let's write it with all the niceties, as some chi tilde, because it's not the standard first order or linear susceptibility of omega here, and EPR omega. So this is like a response of the sample to the electric field PR, the probe field alone. However, the proper expression, because this is of the third order and here is just one order, the proper expression has to contain also the pump pulse, and namely in a square. So this generalized susceptibility depends on EPU and actually to the square power. So this is not a real susceptibility, but it's some sort of a proportion function between these two. The problem here is that we've just stated that we did not really go into the details. So now we have to look into the details of this relation and figure out in what sense we can actually write out some expressions for the chi, because as we will show quickly, it's the chi tilde that we actually detect in a pump probe experiment. Okay, so the detection in pump probe experiment is done so that we detect the E out frequency resolved. So we do the detection of the signal, we actually detect the E out each frequency and we detect its intensity. This is E probe according to definition square, plus now two real parts, and here is the probe pulse and the signal probe, plus something that we can neglect, usually neglect this small contribution, that's basically the signal squared. So if we can assume that the signal squared can be detected with respect to the linear values of the field, then we don't have to take care of this. And what we actually measure is we take a difference between the intensity that goes out and the intensity that went in, and we normalize it to the intensity that went in. It allows us to get rid of the first term and isolate the second term. And not only that, if we look here and here, we have actually E probe square already present. So what we get for this difference is two real parts, kappa I omega epsilon 0 chi tilde, and here we have E probe absolute value square, so it's a real number and it does not interfere in any way with the real part here, and this is divided by E probe omega square, which is again a real number, and these two guys can be cancelled. So in pump probe we are actually really detecting the chi tilde. Well, but the question is, how does it look like? Does it even exist? Because so far for the third order polarization we have an integral expression where there is a function of three variables, the response, and then the electric field, three occurrences of the electric field. So can we actually in Fourier transform really write it this way? So this will be our task after we, let's say, generalize the detection scheme that we have just discussed in detail to something more, well, I don't want to say more useful because pump probe is extremely useful, but something that is a little bit more flexible. So imagine that we would now want to detect, I mean, it sounds stupid if we know, for instance, that in pump probe we can detect the ES, the signal field, alone, linearly, and that we do not have any problem with phases of the pulses. But let's assume that we indeed want to detect a signal field without a background, in a way in which we will have to give it an artificial background, so-called local oscillator, and basically detect it completely independently of the probe pulse, of the third pulse. This will give us more flexibility in a way that we can really separate the two pulses that are in theory inside our first pulse in the pump probe scheme. We will have a flexibility of actually working with two spatial directions for the first and the second pulse in a 3-pulse sequence. The first and the second pulse, they now represent a generalized pump, and there will be still the same probe as before, but the signal will have to be detected separately. So we can basically say, what if we try this? So we will be looking at a more general signal generation, namely the one which is background free. It might now not really look as an advantage after what we learned about the pump probe, but we will see that there are some other advantages which beat the advantages of the pump probe. So let's start with the sample again. We have now two pump pulses going from different directions into the sample. We have a direction K1 and a direction K2, and these two pulses will now be assumed not to necessarily overlap in time. So we will have the first time, the delay between the first two pulses, tau not equal 0, and we have probe pulse. That's the probe pulse. We would normally assume this probe pulse to go through in the direction K3, but the signal now appears in a direction which is different from K3. So this would be the Ks, that's the signal field. So obviously we have no problem to detect the signal in general, so we can directly detect, even of course spectrally resolved, this signal field. But the question is, can we, like in the pump probe, detect the electric field in a linear way? So can we detect ES, not the square but the field itself, or for that matter the susceptibility chi, which actually should be exactly the same in this case, except for the spatial orientation of the signal. So how can this be done? It can be done definitely, but we have to add the so-called local oscillator. We have probably said already that this is a field that is added in addition to all the signal fields and the fields that generate the signal, and it mixes with the signal and provides us basically the same situation as we had in the pump probe, now however in this other direction. So let's introduce the local oscillator field as going together with the signal. So this is the local oscillator field. Okay, we then detect a total field, which is the local oscillator plus the signal, and everything should be more or less the same as before. The E tot in frequency square is the local oscillator square. Local oscillator is a known field. And here we have two real parts of the local oscillator, star and signal electric field star, plus something that we again neglect. And the signal that we detect as a frequency resolved signal is the total signal square minus the local oscillator signal square, and this time we only can normalize it to the local oscillator. We don't have a background actually to normalize it to. So looking at what we measure, we basically get again something like this. But that's not telling us enough yet. We have to now try to see what's possibly the dependence of the signal field on local oscillator. Well, it's clear that there is none, but we can assume, we can hope that the local oscillator is a field similar to the probe. For instance, it can be similar in such a way that we basically first split the probe pulse into two. One of them we send into the sample really as a probe, and the second one we'll use as a local oscillator. This would have the advantage that now the situation seems to be almost identical to the standard pump probe situation. If, for instance, the local oscillator and the probe were of the same intensity, then it would be actually almost exactly the same. And now I'm saying exactly because in such a situation we most likely change the phase of the pulse. The local oscillator pulse would have a different phase with respect to the signal. And as if you remember, actually this phase shift between the probe and the generated signal was what actually defines how the absorption line shape look like. So we may assume this relation between the local oscillator in frequency and the probe pulse. So the probe pulse will be the same as the local oscillator up to some amplitude. That is, the intensity of those two does not have to be exactly the same. And we can have a phase difference between the probe and the local oscillator. So if we assume this, we actually assumed it in a way of defining the probe pulse in terms of the local oscillator, not the other way around. And that's because we would like to get rid of the local oscillator from the expressions above. So we can now assume again that the signal field is equal, because that's why we have the kappa constant here, so that it is equal, is this chi tilde omega e probe omega. And if we put this into the definition of the signal, we get for the signal two real parts. And now of what? Of alpha, we get the local oscillator square. We get I omega kappa chi tilde omega and e to the power of I phi. That's the phase of the field. And we divide this by local oscillator square. So this can be actually divided out. So in principle, as before, we detect chi, we detect the imaginary part of chi because alpha, omega and kappa are real constants. So we detect imaginary part of chi omega, unfortunately up to a phase factor. Up to a phase factor e to the power of I phi. This means that in general, because we don't know what's phi, we don't detect the same signal, same absorption line shape as before. But, well, for the time being, we can just say that this issue can be solved. It can be solved, and we will solve it later. We will do it later. So for now, we will assume that somehow we'll be able to get rid of this phi or set it to 0, and that we can actually really measure even in this so-called heterodyne detection scheme. That's also something we need to say, heterodyne detection. That's this thing that we've just actually discussed. So knowing or thinking that we can isolate the imaginary part of the chi tilde from this experiment despite the problem with the phase, we can go and actually ask what this chi tilde actually is. Importantly, we have some interpretation of this signal from the pump probe. In pump probe, we have we've seen that with ultra short pulses we can understand easily the signals. The signals are composed of just contributions of some Liouville pathways. We have also seen how different Liouville pathways can be weighted with the pulse spectra in order to account for some effects of the finite pulse width. And now we want to do something similar, some similar considerations of what the signal actually is or what we measure in this sort of background free case, with the flexibility of having tau not equal 0. Remember in pump probe tau, the delay between the first two pulses was 0 because there was actually only one pulse. It was only that in our theory we had to take this so-called pump pulse twice in order to get third order signal. Okay, so let's have a look at the chi omega. That means we have to start with the third order polarization in a general formulation. So the third order polarization is a function of running time t and of the delays capital T and tau between the three pulses that are involved here. And in principle we can write this always as this triple integral over delays that actually happen between different interactions of the system with the field, some third order response function, and here the fields t minus tau 3, e t minus tau 3 minus tau 2, and e t minus tau 3 minus tau 2 minus tau 1. Clearly, if t 1, 2, 3 are, or tau 1, 2, 3 are positive, as they are in the integration here, then the last occurrence of the pulses is the one that acts the first, and then we have a second and third pulse interacting sort of sequentially with the system according to some response function, and integral over all these possible interactions builds the third order polarization. Okay, now we will assume, before we've already written E, the electric field, as a combination of three pulses. For now, we don't have to be this careful. For our situation, it would be enough if we split the electric field T, which is a real function, into a complex sort of subfields that represent the positive and negative frequency contribution or frequency part of this real field. So we have always some E plus, which contains e to the power of minus I omega t, where omega is the frequency, central frequency of the pulse. This is the field which is characterized by some wave vector k. And then we also have the second part, which contains plus I omega t, because this has to be real. Then the contributions of the minus I omega t and plus I omega t, they are basically the same. And this is the part which brings the minus k wave vector. Okay, we can also redefine, this will be quite helpful, we can redefine the function so that we put heaviside step functions in front of it. So our S3 from now on, as a function of these times, will be always containing these step functions, so that it will be identically 0 if tau 1, 2, or 3 will be less than 0. So we redefine it this way, and that will allow us to write the polarization basically using a Fourier transform. So we will be able to write the, instead of the 0 in the lower limit of the integral, we will be able to write minus infinity. Okay, so now let's write all the components of the integral here using Fourier transforms. So components of the polarization, we mean this expression for the polarization, so we mean the fields and so on, using Fourier transform. I mean, it will be clear right away what is meant. So for instance, we could write the E minus of t minus tau 3 minus tau 2 minus tau 1, something like this, which will definitely appear in this expression here as a Fourier transform. So we'll take this definition of Fourier transform, e to the power of I omega 1 t minus tau 3 minus tau 2 minus tau 1. Why is this here? This is because if you notice the E minus is the case where we have e to the plus I omega t. That's a negative frequency because the frequency is supposed to be positive in this standard expression. In all optics, we assume we always write with the positive k, we write e to the power of minus I omega t. So that's sort of considered the positive frequency. This is therefore a negative frequency contribution. And here we have e minus of omega 1. That's the Fourier transform of E plus, and it contains a distribution of the frequencies, and it will peak around the frequency omega, which we assume that to be some of this, like the central frequency of the pulse. Okay, we can write, so this was for the minus k1 contribution. We also have plus k1 contribution in some situations, and in that case we would write e to the power of plus t minus tau 3 minus tau 2 minus tau 1. Again, this is going to be 1 over 2 pi integral over some omega 1, and here we would have minus I omega 1 t minus tau 3 minus tau 2 minus tau 1, and here e plus omega 1. And here this is important to say and distinguish, these are distributions of frequencies in the pulse, and the omega 1 that is actually really important here is the one which is around omega, the pulse frequency. So this is the central pulse frequency. Yeah, we say that we have a pulse, even though it is somehow broad, there is a middle frequency of it, and we say we have a light at, for instance, the frequency, I don't know, 12,000 inverse centimeters or something like that. And these E minuses and E pluses, they actually express the distribution of the frequencies that are present in this problem. They express it in terms of spectra or functions of frequency. Okay, so let's have a look what we have. We can now try to rewrite the expression for the third order polarization. I'm dropping all the other dependencies here. We are interested in the dependence on t right now. So what we would have an integral from minus infinity to infinity d tau 3. As we said, we have now redefined the s function, and we can stretch the lower limit of the integration to minus infinity. And this is how it's going to look like for us now. We will concentrate on the part of the integral which contains the integration over tau 1. So this is what we have. S tau 3, S tau 2, S tau 1, e to the power of t minus tau 3 minus tau 2 minus tau 1. So this part we will denote by x, so that we can write that this is equal here again these two integrals and here we have two convolutions. So we will multiply this by an integral from minus infinity to infinity d tau 1, and here is now the rephasing part, rephasing contribution of the response, and here we will have the e minus, because if you remember, the rephasing contribution is such that it first has, I mean, the k vectors are minus k1 plus k2 plus k3. So the first one, first contribution, first electric field contributes with the negative frequency, because it has a negative k vector here. Whereas there is also a second contribution, which will be here plus the integral tau 1. Here is non-rephasing contribution, tau 3, tau 2, tau 1, and therefore we have e plus x minus tau 1 here. And this is the situation in which the first pulse that occurs, the one that is farthest, is actually the k2. So we have k2 minus k1 plus k3. I'm now really respecting the order. This is 1, 2, 3, and this is 2, 1, 3 order of the pulses. It's the first interaction, but now the question is which part of the pulse will be the first. So in this situation here, this is the rephasing situation. Only those contributions which meet, the rephasing part of the response has this dependence on tau 3 and tau 1, roughly such that there is always a minus I omega A. It's an arbitrary transition, and here we have tau 3 minus tau 1. So this meets, this is minus I omega, so altogether it's plus I omega tau 1, and it should meet with the so it's the opposite there. This is I omega minus I omega A tau 1, and that should meet with plus I omega of the pulse tau 1 in here. So, and the same situation, I mean, we have discussed all the reasons why only some contributions from the total response are non-zero. It has always something to do with the cancelling of the oscillating factors from the response and from the field. So basically we can split the two contributions this way, and we can continue by taking, for instance, the first section of it. So we'll just take this part, which we can denote by Roman 1, and we can write it now as an integral over d tau 1 is as rephasing tau 3, tau 2, tau 1, and here we write the expression using Fourier transform. I mean, we write the E minus using the Fourier transform. So there's I omega 1 x minus tau 1 E omega 1. Okay, and we can switch the orders order of integration here. So we will have now what we can identify as a Fourier transform. It's the rephasing tau 3, tau 2, tau 1, e to the power of I minus I omega 1 tau 1, and e to the power of I omega 1 x, and here is the distribution of frequencies in the pulse 1. Okay, and this we will now denote the following way. So we will have the Fourier transform of a function SR, which will now have two time arguments, and the last argument will be Fourier transformed into some omega 1. And here we have e to the power, no, e minus omega 1 and e to the power of I omega 1 t minus tau 3 minus tau 2. Okay, the second contribution, which we can denote by Roman 2, the second contribution will be relatively easy to get. So I will just write it. We would get integral from minus infinity to infinity, tau 1, non-rephasing, tau 3, tau 2, tau 1, and we have the same situation with integrating over omega 1, but now we have minus I omega 1 x minus tau 1 and e plus omega 1, and the result is very similar. Again, integral over omega 1, and there is non-rephasing tau 3, tau 2, omega 1, e plus omega 1 e to the power of minus I omega 1 t minus tau 3 minus tau 2. It is important to realize that these two functions SR of omega and SNR of omega, that they are produced by different Fourier transforms. In one case, it's, depending how you define, it's a forward, and the other one is the backward Fourier transform. The signs are different, but that's the only difference. Otherwise, we have actually streamlined everything up to these signs and plus and minuses. Everything has a very similar form. Okay, so this allows us now to write the P3. I mean, I know that this is a tedious part of the derivation, but we have to keep fighting to get the P3 at the end in a suitable form. So P3, in our next step, we want to handle the integration over the tau 2. So we think about the order of the pulses and how they are supposed to contribute. So looking here, for instance, we can see that the next contribution should be the pulse with E plus, and here in the non-rephasing part there should be a contribution with minus frequencies. So we will write the following: tau 3, tau 2, and here we have E t tau 3 and E plus t minus tau 3 minus tau 2, and the integral that we have derived earlier as r tau 3 tau 2 omega 1 e minus omega 1 e to the power of I omega 1 t minus tau 3 minus tau 2. Okay, this is actually we are here using results that we have derived earlier. We have derived earlier that only the contribution with now negative frequencies is the second one in the construction of the rephasing signal going in the direction of minus k1 plus k2 plus k3 wave vector combinations. So another way how to see this is we will be integrating over tau 2, so we don't want to handle here contributions that are small. So only contributions where some oscillatory factors cancel can produce a decent signal. And here we have an oscillatory factor with tau 2 e to the power of I omega 1 tau 2. So here in the electric field we want to have e to the power of, and this is e plus, so it's going to be I minus omega t minus tau 3 minus tau 2. So if we look at the tau 2 contribution, this one is minus I omega 1 tau 2, and here we have plus I omega tau 2. So these two guys will cancel. The contribution from E minus would have a minus here, and that's why it would not cancel with the oscillatory contribution that is left over from the first integral. Okay, so everything makes sense. We can either find out by what I have just discussed which is the next contribution. So if we have at this position here E plus or E minus, or we simply use the earlier results about in what order the different contributions come for the rephasing or non-rephasing signal. Okay, so the second contribution, the non-rephasing contribution, we can already build by analogy. So we expect that here we are going to integrate the E minus t minus tau 3 minus tau 2. Here we will have an integration with S and R, omega 1 E plus, however, and e to the power of minus I omega 1 t minus tau 3 minus tau 2. And all our discussion from before is valid. Now, let's see what we got here. This equals, now we can already perform the integral over tau 2, because we have this leftover exponential which actually does not belong to the last integral. Well, it does, in fact it does, but we can take this integral over the omega 1 in front of everything. This is the integral, and as I said, we can replace the electric field here with its Fourier transform, and again we put the integration from that Fourier transform to the very front. So here we will be using omega 2 as a variable. So here we have the integral over d tau 3, that's this one, and behind that there is e t tau 3, and I will write here the rephasing response as a function of tau 3. And now let me see what's the argument that we have here. So we have, if we integrate over tau 2, we have this, and we also have in the Fourier transform some omega 2 occurring. So now this is a Fourier transform. If we write for E plus, we have the factor of e to the power of minus I, now omega 2. So inside the E plus, okay, let's write it somewhere here. Inside the E plus, we have, that's an integral over omega 2, and there is e to the power of minus I omega 2 with the argument t minus tau 3 minus tau 2. So here inside we have e to the power of plus I omega 2 tau 2. That's inside the integral by which we replace this e plus. There's this. And then we have again this factor, or this exponential factor, with which we integrate everything. So altogether, if you look at it, the integral over d tau 2 will turn into a Fourier transform of the SR function. And now it depends on how we define that Fourier transform, but we can, for instance, say that this is going to be a Fourier transform with the argument omega 1 minus omega 2. or omega 2 minus omega 1, depending on how you actually define the Fourier transform. So this is, we performed the integration over tau 2, and under that integration, if we replace E plus by its Fourier transform, we get this contribution, and then there will be only exponential factors looking as e to the power of some omegas and tau 2. And we can see that we have an expression omega 1 minus omega 2 present here. And that's why the R, the SR, will appear here as a Fourier transform in the difference of the frequency omega 1 or omega 2. And the direction in which we define the Fourier transform, so whether it's going to be Fourier transform as an e to the power of I omega or minus I omega, doesn't matter here much. So we'll just write omega 1 minus omega 2 here. All right, we still have to close the expression. So we have omega 1 here. And now only the Fourier transforms of E plus in omega 2 and Fourier transform in E minus of omega 1. And we also have to collect the rest of the exponentials. So there's going to be e to the power of I omega 1 minus omega 2 and t minus tau 3. So one of them comes from here, and the other one comes from here. All right, quite complicated. And we have done quite a few steps in one, but let's not be afraid of that. So this was the rephasing part, and there is plus 3 dots for the non-rephasing part. And of course, this was just a sort of side calculation, which we should not mix with the rest of the expression. So this looks like we can continue and perform basically the same thing again with the last remaining time integration, and we can rewrite it in form of a integration over the frequency. So again, it should not be so difficult, so we continue equals. Now I will not do it in detail, but if you look into what we are doing, we again replace the e t minus tau 3 by its Fourier transform. That gives us the spectrum or the Fourier transform of E integrated over some omega 3, and there will be exponentials inside, which we combine with the remaining exponentials here, and we get some Fourier transform in terms of the tau 3 variable and some combination of other variables. And it turns out that we will now have omega 3 minus omega 1 plus omega 2 if we actually choose again the sign of the Fourier transform. So without talking too much, let's write the result. So we get the SR, and here the argument is omega 3 minus omega 1 plus omega 2. Here omega 1 minus omega 2 and omega 1, and we get E plus of omega 3, E plus of omega 2, and E minus of omega 1. And still some exponentials, e to the power of minus I omega 3 plus omega 2 minus omega 1, and the only argument that we are still missing is t, because t still appears in the definition of what we actually calculate. We calculate p3 of t. So everything else was now turned into a frequency integration, and let's write the non-rephasing part also explicitly. So non-rephasing response omega 3 plus omega 1 minus omega 2. That sort of reflects the order of signals. Here we would have omega 2 minus omega 1 and omega 1. Actually, the signs of all these frequency arguments. The overall sign always depends on how we define Fourier transform, and it's not at present very important unless you actually want to really use these expressions for some calculations. E plus omega 1, and here is e to the power of minus I omega 3 minus omega 2 plus omega 1 t. Okay, so this is the full expression for P3, but now using Fourier transformed response functions. And that's not all what we want to do. We would now like to write P3 of omega, because that's what we detect in our experiment. And that is nothing but a Fourier transform of the P3 t. So that equals, and now we have two contributions where the e to the power of I omega t here will meet with this frequency and this frequency. They differ only in the sign of omega 1 and omega 2 because they are rephasing and non-rephasing contributions. So altogether we can now write, this is going to be integral from minus infinity to infinity dt, that's from the Fourier transform, then the three integrals over omega 1, omega 2, and omega 3. And we will have a contribution of the rephasing response. I will not write explicitly all the factors. Here we have the fields, from right to left, the E minus, E plus, E plus. And behind that we have e to the power of I omega minus omega 3 plus omega 2 minus omega 1 of t. And a second contribution which is plus, so let's put it like this, plus non-rephasing pathway with its arguments, and here we have E plus, E minus, E plus. Again, the order is from the right to the left. And e to the power of I omega minus omega 3 minus omega 2 plus omega 1 and t. So the integral that we have here, this integral together with this these exponentials, this will turn into delta functions. Here is the delta omega minus omega 3 plus omega 2 minus omega 1. And here is delta omega minus omega 3 minus omega 2 plus omega 1. Okay, so put everything together, gives me P3 of omega. And now the integrals, d omega 1, d omega 2, SR omega, because this actually we can easily identify as the first argument of the S, SR, and here SNR. So this is the omega, and we integrate over the other two dependencies, which are omega 1 minus omega 2 and omega 1. And here is E plus omega 2, E minus omega 1, and E, because we are replacing omega 3 here, it's going to be E plus omega minus omega 2 plus omega 1. Now we are actually solving this condition here for omega 3. And the second contribution is an R omega 2 minus omega 1 and omega 1, and E plus omega 1, E minus omega 2, and here we have E plus omega minus omega 1 plus omega 2. That's a very important result. That's sort of close to our final result. We have now been able to write the p of omega as a function really of omega, but there is an integration over the pulses. And that integration not only involves the first and second interaction, but also it involves the E plus from the last pulse. But if you remember, we were asking whether I can write the P3 of omega as chi omega E of the probe, that is the last pulse. So this was our question, can I write it like this? And we were actually always assuming that we can. But now we see that this is not possible in complete generality. Luckily, there are some good reasons or two situations in which we can hope that at least approximatively there is a chi of omega, that it exists, and that we can use it to our advantage and actually measure. So one situation is, imagine our first sort of idea of how we make a frequency resolved pump probe spectroscopy. I mean, excitation frequency resolved. In that case, we were assuming that we are exciting with very narrow pulses. So if we have narrow pulses, I mean frequency narrow in omega, narrow pulses, that means that in the integrations that we have here, omega 2 is actually roughly omega, and omega 1 is also roughly omega. These are the, let's say, the pump frequencies. So if there are narrow pulses in omega, so this is the omega pump, then clearly omega 2 is similar to this omega pump, and it's therefore similar to omega 1, and we can say that E plus omega minus omega 1 plus omega 2, for instance, is roughly E of omega, E plus of omega. So interestingly, due to and thanks to the narrow excitation pump pulses, it seems that in our expression for P3 we can ignore the fact that the E probe has to be integrated also over omega 2 and omega 1, and we seem to have in this case truly although approximatively this expression, there is chi omega E plus omega, which is fine, which is what we wanted. So it seems that our initial idea of how to do this frequency resolved pump probe or two-dimensional pump probe spectroscopy, where if we let's say scanned the excitation frequency, that it would work. But that's a method in which we did not overcome at all the problems with the temporal, with the competition between the temporal and frequency resolution. We did not win anything over the normal pump probe, or this is the normal pump probe. So what else can we do? Where is the other possible way of turning this expression into what we want, into actually detecting some chi tilde? Well, luckily, it seems that there is another reason why the ansatz that we were actually so keen to use before already, that it works. Well, in principle, if we look at how the SR depends on omega 1 and omega 2, we figure out that already this function is actually making sure that omega 1 minus omega 2 is close to 0. So we have another reason why this might work, and that's the properties of SR and SNR functions. Namely, let's have a look at how they depend on time. So this is a sum of response functions corresponding to individual Liouville pathways. And they always contain the elements of the evolution superoperators. There are elements of evolution superoperator in tau 3, evolution superoperator in tau 2, and evolution superoperator in tau 1. And these first two occurrences, or let's say the occurrences on the sides of these expressions, these are usually some elements G, N, ground state, and some excited state. And here we have, let's say, MG, that's also ground state and excited state. Because this is rephasing, we have to respect the fact that the rephasing diagrams, they always start with interaction from the right. So here we have the excited state N and G, and against it, here on the other side, we have the MG. That's a rephasing signal. I mean, the interactions in the middle can be whatever, but it's clear that these U tau 3 and U tau 1, those are functions that contribute with these fast oscillating frequencies. G, I think like this, in fact, and here we have I omega n G tau 1. So these clearly are those fast oscillating things that we have turned into something interesting by Fourier transform, and that Fourier transform is centered around some fast optical frequencies. But what about the thing in the middle? This is the evolution of populations of the excited states, for instance, or some coherences also between two excited states. So I have this situation, I have a bunch of excited states, I have optical frequency omega, on which these two exponentials oscillate, and then I have the middle U tau 2, which does not oscillate at all when it comes to population of one state, or oscillates with a much slower frequency when it comes to coherence between the two excited states. So because U tau 3 and U tau 1 are fast oscillating functions, their Fourier transform is centered around some high frequencies, but the Fourier transform of the U tau 2, the middle interval, is centered around the frequency 0. So that's an important result. Here the corresponding frequency, let's call it omega dash, is actually around 0. And with that, we can assume that the function SR, and now whatever this is here and here, omega 1 minus omega 2, and here whatever, is actually almost independent, or it peaks around, this is omega 1 minus omega 2, it peaks around 0. It peaks around 0 and it enforces omega 1 roughly to be the same as omega 2. And that's the second reason why, in fact, I can write an approximation for the P3 omega and assume that it really has the expected form of P3 omega equal chi delta omega and the electric field of omega. So let's summarize it here. For those two reasons, we can actually set E plus of omega minus omega 2 plus omega 1 to be similar to omega minus omega 1 plus omega 2, and to be the sort of similar as E plus omega, and the assumption, the form P3 omega equals chi tilde omega E plus omega is valid. Very nice. And we can also write now what is the chi tilde chi tilde is this double Fourier transform of SR of omega 1 minus omega 2 omega 1 E plus omega 2 E minus omega 1 plus SNR of omega 2 minus omega 1 E plus of omega 1 E minus of omega 2. And clearly because the electric fields here, they have some phase given by the delays between them. This is the chi tilde omega with dependence on capital T and tau. And that's our measured signal. So the time-dependent signal is this Fourier transform, but in fact we are actually measuring this original frequency-dependent chi omega in our heterodyne detection scheme. Okay, so the only thing that we have to do now would be to, in our expressions here, we do not recognize well the role of capital T and tau, so it would make sense to take the chi tilde with this definition and write it again in the time domain. So let's use the definitions that we have. Chi of omega equals, so first we will have to write the response function as a function of times now in the second and the third argument. So we will have to introduce an integration over some tau 2 and tau 1. Here we have the original integration over omega 1, omega 2. So it's going to be S R omega tau 2 tau 1, but e to the power of minus I omega 1 minus omega 2 tau 2 and minus I omega 1 tau 1. So this together makes the Fourier transforms in the second and the third argument of the response function. And then the expression continues by replacing the spectra of the pulses by the Fourier transform expression. So we basically write something like this. Here's some tau dash e plus tau 2 dash e to the power of I omega 2 tau 2 dash. So this is how we handle the e plus, and e minus would be handled by this Fourier transform. This is tau 1 dash e to the power of minus I omega 1 tau 1 dash. Okay, so if we put together the exponentials now in omega 2, so here and here, that's all, and in omega 1, which is here and here, we get some delta functions. Actually, we would still have here the integrations over all the time variables, tau 1, and here we would have d tau 1 dash and d tau 2 dash. There will be SR omega tau 2 tau 1, and here delta function of tau 2 plus tau 2 dash and delta function of tau 2 plus tau 1 plus tau 1 dash, yeah, because the omega 1 has tau 2 and tau 1. k, and electric field of plus at tau 2 and electric field of minus at tau 1 with the dash. And of course something similar for the rephasing part. So here I also should not forget that we are ignoring the non-rephasing part because it's going to look basically the same. So now we are getting to a somewhat surprising expression. It shouldn't be so surprised because we are missing all the expressions in which before we had t. So this is integral over tau 2, integral over tau 1. We got rid of the other two integrations by taking into account the delta functions. So we have SR of omega, tau 2, tau 1. So this has come out as before. And here is E plus of minus tau 2 and E minus of minus tau 2 and minus tau 1. That comes from the delta functions. This is somewhat suspicious, but we will clearly be able to identify what that means. Tau 1, and for the non-rephasing part we would get something similar, except that the first pulse that comes is the one with plus, the one most on the right, so and the second is the minus. So this looks strange until we realize what is missing. What is missing here is the expression t minus tau 3, and also here we should have t minus tau 3, and here is t minus tau 3, and here is t minus tau 3. If we had this, it would look perfectly normal, except of course that this is Fourier transformed. The fact that it's missing, it's a result of the approximation that we have made. Here are high above. That's where we neglected here the dependence on omega 1 and omega 2. That's how we got this result. And what does it then mean? Well, it means here that the approximation that we have made is actually quite consistent with the assumption that t minus tau 3 is 0. That is basically an assumption of an ultra short, that is spectrally very broad, infinitely broad last pulse of the sequence. So this is the probe pulse is infinitely short. This is no surprise because we kind of assumed this from the beginning, that we probe with a very broad pulse. Okay, so this therefore tells us that when we detect the signal in the heterodyne detection scheme, we basically detect what we want. We detect this chi tilde, which is basically the response functions weighted by the excitation pulses. That's quite important, and the assumption that we are making implicitly, somewhat implicitly, is that the last pulse is very broad. In fact, ideally, all pulses that we use would be spectrally as broad as possible, because then we would have no overlap effects, and we would be measuring an ideal signal as a function of omega, that is here explicit, and implicitly as a function of the delays between the first two pulses and the second and the third pulse in the sequence. So we can kind of conclude that we detect the real part of I chi tilde e to the power of I phi, which is well, one can see that this is minus imaginary part of chi tilde with this phase factor, which is, when we look at how this is all expressed in terms of Liouville pathways, this is minus imaginary part, and here the Liouville pathways, they all have this I to the power of 3 prefactor. So here I'm summing over all Liouville pathways, and of course the phase factor. And ultimately this means that, because the I to the third power here is minus I, ultimately this means that we are detecting a real part of the sum of Liouville pathways, maybe weighted by the pulse spectra, etc., but modulated by this phase between the signal, or between the probe pulse and the local oscillator, something that is kind of hard to estimate, but we will see that there are ways how we can do it. So, the conclusion is that we detect Liouville pathways, always the sum of either rephasing or non-rephasing pathways, because we can measure positive and negative delay between the first two pulses, that is pulse 1 with K1 first and K2 second, or K2 first and K1 second. This can be arranged, so we can detect Liouville pathways up to the phase factor. And because we said that we can handle this, or we will handle this later, let us now have a look at what happens when the phi is equal 0. So what can we achieve with this? So if we manage to get rid of the phase problem, we are left with basically detecting real parts of the Liouville pathways, or the contributions corresponding to Liouville pathways. So we detect a quantity which depends on 3 times and is proportional to some orientationally averaged factor containing 4 transition dipole moments. Let's not go into the details here, but then there are these elements of the evolution superoperators. Here we have, I keep writing it like this, with specifying only the states in the first and the third interval. So this is the rephasing pathways. So once we can detect this, that is, we got rid of the phase problem, it only depends on the properties of these response functions, what we can learn from them. I mean, if we find something interesting in them, well then, nice. We can use it to learn about the systems that we measure. So first of all, this is the definition of the pathways. We don't detect that, we detect something else. So we detect this thing Fourier transformed, and we detect the real part of it. So we detect something like this, which is again quite symbolically here the real part of the like half Fourier transform in T. Okay, and here we have ut and ug and g and tau. So now this first part we already know, this we have defined somewhere. This is the complex line shape GMG of omega. It's the complex line shape. Real part of the complex line shape gives us absorption spectrum, basically. So now, assuming that we have capital T and tau equal to 0, then real part of R omega 0, 0 is something like this. Real part of G mg omega. This is the absorption line shape, so this is basically pump probe at t equal 0. The important thing is that this here is the absorption line shape, which is no more complex. It's real. Let's call it alpha of omega. All right, we can have a look now, and that brings the most to us. Actually, have a look at this last term here, which has many similarities with the first term. I mean, in terms of order of physics, this is the red term is the first and the blue one is the last, but we read it from left to right. So the term with tau has many similarities with the term with t. In fact, we can write the following, we can use the following kind of definition. Actually, if we take a Fourier transform, again half Fourier transform of the gn tau, and take it the Fourier transform with minus omega, here we define some omega tau. This would be the line shape g and g of omega tau, but complex conjugated. Now we can add one more speculation to our sort of speculative development of a possible new spectroscopic method. Can we actually detect complex signals? Well, the speculation is that we can. So what if we can detect complex signals? I mean, clearly the electric field or the intensity that we detect is real, but the question is whether we can detect response functions that are complex in some way, and we will see later that this is possible. We can actually detect the rephasing response functions Fourier transformed as functions of t and tau as complex values or complex values quantities, and if we put on them the Fourier transform from above, actually writing it like this, assuming that of course in tau we explicitly assume here a step function, because we redefined the response function so that they contain the step function, we would get something like this, a response function Fourier transformed in two frequencies. Okay, and this would actually be this prefactor with the dipole moments and a complex line shape, for instance like this. You know, I'm adding just randomly here the indices of the transitions, but obviously we are summing always over all such transitions, and here on the most right hand side we would get this complex conjugated complex line shape. Okay, so this is something that we can create from the rephasing pathway, but it's important to realize that there is also non-rephasing contribution to the same signal. So this is rephasing contribution Fourier transformed based on rephasing pathways, and let's have a look at the non-rephasing contribution. Here we will define the Fourier transform differently, because the last argument of a non-rephasing pathway is not a UGN but UNG, and we don't have to have any complex conjugation in there. So this we will Fourier transform in a usual way, or with a positive sign. So we take this e to the power of I omega tau, and this would correspond to d for g mg ut, and here we will have complex line shape and g without complex conjugation, and that immediately can give us the following idea. So combining these two together, we'll get an absorption line shape on the most right hand side. So combining rephasing and non-rephasing signals. If we do it with equal weight, that is rephasing pathway Fourier transformed like this, and non-rephasing pathway Fourier transformed like this, this should give, if you look at it, it's a sum of contributions that are the same. Here we have the initial contribution that is the same, and then we have a sum of G star plus a G. That's twice the real part of the G. So here I can write real part of G and G omega tau, which is nothing but absorption in omega tau. All right. And now, assuming that U is real valued, because most of it will be transitions between states and etc. Of course, there might be some small contribution also from oscillating coherences, but if we ignore that, by taking real part of the same expression, real part of the sum of these Fourier transformed contributions, well, we'll be actually getting D4. It's actually only symbolic calculation. We're taking the real part of GMG omega ut and here alpha omega tau, and this first real part, because this part here ut can be considered real if it's about populations. This here is also absorption spectrum, and this time in omega. Well, this is absorption spectrum of the transition N, and this is absorption spectrum of the transition M. So if we could indeed detect the complex signal, and if we were able to put together a rephasing and non-rephasing signal of the same kind, we would basically get absorption spectra in the detection frequency omega and in a Fourier transform of the delay of the two pulses. These two absorption spectra are connected by the evolution supraoperator elements. So we can detect absorption spectra of different transitions connected by evolution of excited state populations. This is actually, well, a bit too short, this explanation. We will have to go into details into what different contributions actually mean, or how we can organize them into a meaningful spectrum. But here it's already clear that by combination of different signals, we are able to produce a product of absorption spectra in two different variables. So it would be like correlation of absorption on the, let's say, transition N with the absorption on the transition M, but it's all connected by an evolution superoperator. So what does that mean? So let's define our signal now in some better way. So if we can detect complex rephasing signal, complex rephasing signal would be actually whatever we detect when we measure with positive tau. So let's call it sigma r. That's what we have on the detector. It depends on omega. Let's denote that omega with small t, because that's basically Fourier. On the detector we are making a Fourier transform of the time t, that's the real time. Then there are two delays here, and this is measured with the order of pulses 1, 2, 3. This is order of pulses. k minus k1 plus k2 plus k3. Then we measure complex non-rephasing signal. That's when the delay tau is smaller than 0, which means that the order of pulses is 2, 1, 3. We usually actually work with tau positive, just switch the order of the pulses. So we have some sigma non-rephasing also as a function of omega t and capital T and tau. So we combine these things into so-called two-dimensional coherent spectrum. Let's denote it this capital theta omega t capital T omega tau. And how do we get that? Well, we get that by Fourier transforming the tau variable. So this is integral from 0 to infinity d tau sigma r omega t capital T e to the power of minus I omega tau tau, and we add to this integration over absolute value of tau sigma non-rephasing here omega t absolute value of tau e to the power of I omega tau absolute value of tau. I just put absolute value because we want these things to be positive. Okay, so this would be a new spectrum, two-dimensional spectrum, and the question is how this spectrum looks like. So from what we know so far, it has to be proportional to a sum over all possible transitions that we can see in our system, and there would be, for possible transition, dipole moments involved here, averaged over the spatial orientations. And here we would have absorption spectrum of some kth level. That's the last one. That's the last interaction with the field, or last transition that we have in the diagram. Here in the middle, we would go from the initially excited nth transition. We would go from here, that there would be, if this is rephasing, well, it doesn't matter, this is anyway just an attempt to explain what is the signal composed from, but we will make more detailed prescriptions of how to calculate the spectrum. So we first excite, for instance, to state n, and then by the second excitation we'll excite to the state m. So we would have coherence mn, which would transfer to coherence kl, k and l, or and m can be easily the same. This depends on t. So this is basically how we can expect the spectrum to look like. This is two absorption spectra in different variables connected by the evolution superoperators, and the largest contribution will come from the evolution of populations, so that we would roughly have a sum over some states n and k, and here there will be dk square and dn square averaged, and here we would have the transfer from state n to state k as the time progresses. And of course this spectrum can be already easily drawn. Let's have a look at the situation at capital T equals 0. In that case, the u, k, k, n t is nothing but delta k n. It is 1 when k and n is equal, and in that case we would only have a sum over each transition that is present in the system, and each transition will just show with its absorption spectrum. So there will be these absorption spectra on one axis. This is omega, this is actually omega tau, this is omega t, and here we will have the absorption spectra, and if we combine them together, their products would look like here with contour plots. We would see two-dimensional line shapes sitting on the, let's say, diagonal of this two-dimensional spectrum. So here's the diagonal line. Now, of course, what can happen and what is important that it happens is that the time t evolves, t larger than 0, and it would mean that the elements of the evolution superoperator, the elements u, for instance, if we say this is 3, 2, 1, states 3 to 1, so we could have elements 1, 1, 3, 3 at capital T larger than 0, also larger than 0, and u 2, 2, 3, 3, t also larger than 0. So what we would have then here? Well, in fact, we would still have, at least if the situation were as it is described here, we would still have the same signal sitting at the first and second transitions, but we would have, because of this increase of u1, 1, 3 and u2, 2, 3, we would also have to have a decrease of u3, 3. We would have less signal here at the top, and we would have some signal depending on the on how large these elements are. We would have some signals here. So we could observe so-called cross peaks due to energy transfer between states, due to relaxation of energy. And now you see that we have a correlation plot which tells us, for instance, in this case here, we note that the excitation started at omega 3, that's this, and was emitted, or actually the signal was emitted, so it ended up on omega 1. So we have clear information about where the excitation started and where the excitation actually led to an emission of a signal. Both the emitted signal and the signal corresponding to excitation looks like an absorption spectrum. That is no problem, but in our plot we have exactly the thing that we hoped to get in our pump probe with narrow pulses. The problem with that was that there was an intrinsic problem with the fact that the pulses had to be long, but now ideally the pulses would be extremely sharp, extremely short, so they would be brought in frequency domain. So there's no problem with time resolution, but up until now, until we actually learned how to Fourier transform this third interval here, which was impossible in pump probe, we couldn't get simultaneously a frequency resolution, but these plots are perfectly frequency resolved. We still have a couple of tasks to do because we came with this type of spectroscopy under two conditions. We have to be able to detect complex signals. We have to have complex values for those signals that come from different Liouville pathways so that we can properly Fourier transform them. And we also have to be able to get rid of the phi. And if we successfully overcome these two problems, we will have a perfect spectroscopy which will have both frequency and time resolution. And to get that, we will try to overcome these two problems in the videos that will follow.